المبعوث رحمة للعالمين.
Right. Now, besides that, let's simplify for just a moment and consider now the world of chars. If we've just got single bytes, where does this lead us, and how does this get us ultimately to strings to solve problems like readability and cryptography and the like? Well, here, for instance, are 3 lines of code out of context that simply store 3 chars. And you can already see where this is going. Having 3 variables called C1, C2, C3 is clearly going to end up being bad design because of all the silly redundancy here. But notice I'm using single quotes like last week because these are single chars. What does this look like in the computer's memory? Well, it looks a little something like this. If we clear out the old memory, C1, C2, C3 probably will end up here. Maybe not literally in the top left-hand corner. This is just an artist's rendition. But C1, C2, C3 will probably end up like that. Now, what's really there? It's really those same 3 numbers, 72, 73, 33. But how many bits does a byte have? Just 8. So if we were to look at the binary representation of these characters, it would only be 8 bits each. That's enough to store small numbers like 72, 73, 33. We're not dealing with Unicode and emoji and the like. But the point is the same. You don't have to use 4 bytes to store these numbers. You can use a different data type like chars. And underneath the hood, it's indeed going to use just single bytes for each. But this is sort of like this isn't really how we implement strings, right? When you wanted to say hi last week or this, we used double quotes. And we wrote all of the things together and used 1 variable, not 3, right? When I typed in David, I didn't have a variable for D, A, V, I, D. I had 1 variable called name that stored the whole thing. So in C, we keep talking about these things called strings. We'll see eventually that strings are not necessarily what they seem to be. But for now, the key thing about strings is that they're variable length, so to speak, right? They might be 3 characters, hi, or 5 characters, David, or anything smaller or larger. So how do we go about implementing strings if all we have at the end of the day is my memory? Well, here is an example of just creating declaring and defining a string called s. S because it's just a simple string, and quote unquote hi in double quotes. What does this look like in the computer's memory? Well, let's clear it again. And here now, because it's technically stored in 1 variable s, here is how I might draw it as an artist. It's 3 bytes in total, hi exclamation point, but there's no C1, C2, C3. It's just the whole thing is s. But it turns out that a string, fun fact, is really just what underneath the hood? Kind of leading up to this. What is a string if this is how it's laid out in memory? Literally, it's just an array of characters. And we didn't have to know about arrays last week to use strings. This is where, again, the training wheels are starting to come off. But a string is just an array of characters, hi exclamation point, for instance. So technically, an array, or a string called s, is really a variable called s that allows you to get at the first character with s bracket 0 if you want. S bracket 1, s bracket 2. You can literally get individual characters just by treating s as though it's an array, which it really is underneath the hood in this case. But there's a catch. How do you know where strings end? In the past, when I drew some integers on the screen, I claim they always take up 4 bytes. If I had drawn a long, it always takes up 8 bytes. If I had drawn a character, it always takes up 1 byte. But how many bytes does a string take up? Yeah, I mean, that's kind of the right answer. In this case, 3, it would seem. But if it's David, that's a good 5 characters. But where do we put the number 3? Where do you put the number 5? Right? This is literally all that's into your computer. This is all our building blocks in front of us. So where does the 3 go? Where does the 5 go? Well, it turns out you can solve this in a couple of different ways. But the way humans decided to implement strings years ago is indeed an array. But they added 1 extra byte at the end of every such string array just to make clear with a so-called sentinel value that the string ends here. Why? So that if you have 2 strings in the computer's memory, like hi and bye, you know where the barrier is between like the exclamation point of one and the letter B in the next, right? You need some kind of delimiter. And so what really is underneath the hood is this. When you store a string in memory, when you type in a string as the user, if you type in 3 characters, it's going to use 3 plus 1 equals 4 bytes in total. If you type in David, it's going to use 5 plus 1 equals 6 bytes in total. Why? Because C automatically adds this special 0 at the end of the string. I've drawn it with \0 because this is how you represent 0 as a char, as a character. But this is literally just 0, as we'll soon see. So anytime there's a string in memory, it always takes up one more byte than you yourself as the programmer or human typed in. In fact, if we convert this again, just for discussion's sake, to those integers, what's literally stored in the computer's memory is going to be 72, 73, 33. And now a 0. And the computer, because of C and how it was invented, it's just smart enough to know that when you print out a string, it prints out every character until it sees a 0, and then it just stops printing. In particular, printf knows how this works. And this is why printf knows when to stop printing. Decimal numbers are not that enlightening. We'll generally write the characters like this. And again, \0 is just special symbology, like it's what the programmer types to make clear that you're not saying hi 0. You're saying hi, and then it's a special 0. Specifically, it is 8 0 bits that indicate that it's the end of the string. Technically, that \0, if you want to be fancy, it's called null, N-U-L. And it turns out you've seen this before, though we didn't call it out. Here's that same ASCII chart from the past couple of weeks. If I highlight this, what is decimal number 0 mapping to? NUL, which is just programmer speak for the special null character. All 0 bits, that means the string ends here. This all happens automatically for you. You do not need to create these null characters or these zeros. Any questions then on this implementation thus far? Any questions here? No? Well, let me do this. Let me go back to VS Code in a second, and let's actually corroborate this with some code. Let me go ahead and create a small program called hi.c. And how about we do this? Let me include standardio.h. Let me type out int main void as always. And now let me do something simple and kind of bad, but char c1 equals quote unquote h in single quotes. Char c2 equals quote unquote I in single quotes. And lastly, char c3 equals exclamation point in single quotes. And now let me just print this out. I can't use %s because that is not a string. That's literally 3 chars because that's the design decision I made. But I could do this. %c, 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 which we haven't seen before, but %s is string, %i is int, %c is indeed char. So let me put a \n at the end for cleanliness, and now do c1, c2, c3. So this is like a char-based version of printing strings. So let me make hi, and then let me do /hi, and it looks like I used printf with %s. But I did things very manually by printing out each individual character. What's cool now, though, is that once you know that characters are just numbers and strings are just characters, you can kind of poke around. Let me change all 3 placeholders to %i instead. And this is totally fine, too. Let me rerun this. Make hi, actually, let me make one change just so we can see this. Let me add spaces just for aesthetic's sake. Let me do make hi, /hi, enter, and voila. Like now you can actually see the numbers that I claimed back in week 0 were in fact happening underneath the hood. Well, this is not how you would make strings. It'd be incredibly tedious to have 3 variables for 3-letter words, 5 variables for 5-letter words. We've been using, of course, strings since last week, so let's do that instead. String s equals quote unquote double quotes hi. For this, no, because of these training wheels, I need to include the CS50 library, but we'll come back to that in the coming weeks. But for now, I'm going to go ahead and create a string s called quote unquote hi. And now I'm going to change this to be my familiar %s, and now just print out s itself. This, of course, is the same thing as last week. /hi gives me the exact same thing. But now we're dealing, of course, with strings. But how can we see a little beyond that? Well, how about this? Let's poke around further with today's primitives. Even though s is a string, I could technically print out its first character with %c by doing s bracket 0. I could technically print out its second character with %c by doing s bracket 1. I could print out its third character with %c and printing out s bracket 2. So again, this just derives logically from my understanding now of that strings are arrays, as you note. Let me do make hi, /hi, and no visual change, but I'm just kind of now tinkering around. And in fact, if you're really curious, let me do this. Let me change these back to I, back to I, and let me add a 4th one, because if I'm really curious now, let's see what's at s bracket 3. This is the 4th byte, and even though the string itself is hi, I think we can corroborate this whole null thing. Make hi, /hi, enter, and there it is. You could have done this last week if you really wanted to geek out on strings, but like for now, it's just revealing what's going on underneath the hood. Questions then on what these strings are? Yeah? Why do we need the bracket? Why do you not need brackets? Good question. Why do I not need brackets on line 6? Because S is a string. We'll see in a couple of weeks that S is essentially implemented underneath the hood, indeed, as an array. But that happens automatically for you. You can treat S as just a variable name without square brackets. You will use square brackets when you have arrays of ints, or you manually create arrays of chars, or doubles, or floats, or anything else. But strings are special. Why? I mean, every program you write seems to use strings, text in some form. We're humans. We like text, not just numbers and such. So this is just treated a little specially in C and many other languages as well. All right. Other questions on this here? No, let's add then one other string to the mix. So instead of just saying hi, why don't we consider a version of the program that says both hi and bye? And I claim now that that \0, that null character, is going to be ever more important now if we've got 2 strings in memory so that C knows how to distinguish one from the other. So let me go ahead and just get rid of these 2 lines for the moment. Let me recreate string S equals, quote unquote, double quotes, hi. Let me give myself another one. And because I'm just playing around, I'll choose very short variable names. String T equals, quote unquote, bye, exclamation point. And then let me just print them both out. Let me go ahead and print out %s, \n, comma s, and then printf, %s, \n, and then t. So very simple demonstration of just these 2 variables, make hi, /hi, and of course it prints out 2 lines, one after the other. What's actually going on underneath the hood? Well, let's go back to the computer's memory. Hi, I think, is going to be, I claim, pretty much the same. So S, I'll claim, is in the top left, followed by the \0, and that's important now because bye probably is going to end up there. And visually it wraps just by nature of how I've drawn this grid of bytes, but it's contiguous. B, Y, E, exclamation point, null, aka \0. This is now helpful to printf because now printf knows where one begins and ends by way of that special null character. But we can poke around now too. What else can I do here? How about this? How about I go into my code here, back to VS Code, and let me go ahead and say something like, well, if I've got 2 of these strings, let's put them in an array. Let's kind of do this sort of arrays in arrays, sort of Inception style here. So string words, bracket 2. So give me an array of 2 strings is what I'm saying here in code, even though we've not done it with strings yet. We only did it with ints. And now let me do this. The first word, aka words bracket 0, will equal, as before, hi. And now words bracket 1 will equal, quote unquote, bye. Bytes. So bye. And now I've done the exact same thing. But again, I'm just avoiding having S, T, Q, R, and like all these different variables in my code. I just now am treating them as one single array of strings. How do I change my code down here? Well, if I want to print the first word, I do words bracket 0. And if I want to print the second word, I do words bracket 1. This is not a useful exercise at the moment because I'm just making my code more complicated. But again, it allows us to poke around and see what's going on because there's that hi and bye. But watch this. If I really want to be cool, I can do this. Let's print out %c, 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 \n. And then here, %c, 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 %c. So 4 of those. And now, here's where things get interesting. Words is an array of strings. But again, if I may, what's a string? An array of characters. So just use the same logic. If words is an array of strings, you get at the first string with words bracket 0. How do you get at the first character in the first string? Bracket 0. Words bracket 0, bracket 1. And lastly, words bracket 0, bracket 2. And now down here, words bracket 1, but the first character is there. Words bracket 1, the second character is here. Words bracket 1, the third character is here. Whoops. third character's here, and words bracket 1, the fourth character is here. Like, this is not how people program. This is only for demonstration's sake. My God, it's so tedious and verbose already. But if I make hi now, /hi, now I'm like manually reinventing %s if I forgot it existed using %c alone. But you can indeed manipulate arrays in this way. But because strings are arrays of characters, you can manipulate strings in this way too. Any question now on this syntax? Any questions here? No? All right. Well, let's go ahead and propose that we solve a couple of other problems we might not have as before. But first, a quick visual of what's been going on underneath the hood here. If here again is where we left off on the screen, hi and by back to back, here is really how I just treated these things. S bracket 0, 1, 2, 3, and then T 0, 1, 2, 3, 4. But really, once I put them in an array, the picture becomes this. Words bracket 0 is the whole hi. Words bracket 1 is the whole by. But if I really get into the weeds and start indexing into individual characters in those strings, all I'm using is new syntax in order to represent these same values here. Questions then on these representations before we forge ahead? No? Yeah. Does the new line character, say that once more? Really good question. Does the new line character take up any space? It does when, so far as printf is concerned, but I'm not storing the \n in my strings. Printf is being manually handed that thing instead. All right, so let's go ahead then and consider how we might solve some problems that have arisen now with these strings as follows here. Suppose let's do this. Let me go back to VS Code here, and let me go ahead and open up a new file called, how about length.c. And let's consider for a moment how I might actually figure out what the length of a string is, which is distinct from the length of an array. I claimed earlier you cannot figure out dynamically what the length of an array is, but I can figure out the length of a string specifically because of this implementation detail of that null character. So let me go ahead and do this. Let me include CS50.h in this second program here. Let me include standardIO.h as before. And let me do this. Int main void. And in the first thing I'll do is just get a string from the user. I'll ask the user, as always, for their name. So I'll call getString and say, what's your name, question mark, as always. And then down here, if I want to figure out the length of this string and print the name, print the length out on the screen, well, I can kind of do this similar in spirit to the average, where I'm accumulating something. Let me go ahead and initialize n to 0. Let me give myself it's not a for loop because I don't know in advance how long it is. But what if I do this? While the value at name bracket n does not equal single quote \0. Crazy syntax at the moment, but it's just the culmination of these various building blocks. Let me just finish the thought here. N++. And then down here, let's just print out with printf and %i that value of n. So I claim this is going to show me the length of any string I type in, whether it's hi or by or David or anything else. I initialize a variable to 0. And that's good because that's where you start counting in general. While name bracket 0 does not equal \0. What is this saying? Well, if name is the string the user typed in, and name is just an array, as you noted, then name bracket 0 is going to be the first character. And I'm asking the question, well, does the first character not equal \0? And if I type in David, D, it's not. So I keep going, and I add 1 to n. Then I'm going to check name bracket 1. Well, if I typed in David, name bracket 1 is going to be A. A does not equal \0, and so it's going to go again. And again, and again. But 5 steps in total later, it's going to get to the byte after DAVID, realize, wait a minute, that is a \n. The loop finishes, and I print out the total length. Arrays in general do not have this null character. However, strings do. Again, strings are special versus all of the other data types we've talked about thus far. But how could I, for instance, do this differently? Well, let's actually factor this out as a function, as I've commonly done. But rather than implement it myself, you know what? It turns out what's nice about strings being so common, there are many other people who have solved these problems before. And in fact, there's a whole string library in C. It is used by way of a header file called string.h. And what string.h is a library of string-related functions. In fact, you can see in CS50's manual pages for C, the string.h functions, at least those that we recommend as most useful. And in particular, if you poke around there, you'll see that there's a function called strlen. Means string length. It was named very succinctly just because it's a little easier to type than string length. But strlen tells you the length of a string. So how might I use this in my code here? Well, it turns out I can simplify this quite a bit. Let me get rid of my loop, get rid of my, my counting manually, and do something like this. Int n equals strlen of the human's name. And now I'll just use printf as before with %i\n and output the value of n. But there's a bug at the moment. What have I forgotten to do? Yeah, I have to include the header file at the top of the screen. So let me, at the top of the code, so let me also include string.h at the top of my file so that C knows that, in fact, strlen exists. Let me go ahead and make length as before, /length. Or actually, really for the first time, what's your name? DAVID. And hopefully, I'm going to see, in fact, 5. By contrast, if I run it again and type in hi exclamation point, now I see 3. So strlen is just one of the functions in that library, and there's so many more. In fact, yet another library that might be useful moving forward is this one, ctype, which relates to C data types and lots of functions therein that can be useful. For instance, if you review its documentation in the manual pages online, you'll see that there are functions via which we can solve problems like this. Let me go ahead and propose here. Let me see. Let's do example here involving how about checking if something is uppercase or lowercase and converting it to uppercase only. Let me go back to VS Code and code a program called uppercase.c. In this file, I'm going to start by including now, as always, CS50.h. I'm going to include standardIO.h. And I'm going to add one other to the mix, which is string.h now too. So I can access the length of things as needed. Int main void comes next. And then within my main function, I'm going to go ahead and declare a string called s. I'm going to call getString as before. And I'm going to go ahead and just ask the user for a string called before. I want to do a before and after. Whatever the user types in is before, but I want to force everything to uppercase thereafter. Let me now, in this loop here, do this. Let me printf, quote unquote, after, just so we can see this on the screen. And let me do for. Int I gets 0. I is less than strlen of s, I ++. What am I about to do? I'm about to iterate over every character in the string from left to right, from 0 on up to, but not through the length of s. And how do I check if something is lowercase so that I can actually force it to uppercase? Well, it turns out I could do this literally. If the character in s at location I is greater than or equal to capital A, ampersand, which means and instead of or, which we saw in the past, s bracket I is less than or equal to little z, that means logically in English that this is indeed lowercase. How do I now convert it to uppercase, this character? Well, I could just literally print out the same character, but that would not be the answer here, because that's not changing the value. But what could I do instead? Well, let me actually pull up here real fast the ASCII chart as before, and let's see if we can't glean some insight. If I pull up the same ASCII chart, and suppose the human has typed in a lowercase a, that's 97. What letter, I want to convert it to uppercase A, so what number do I want to convert the 97 to per week 0? So 65. We keep coming back to that one. What if the user types in lowercase b? I want to change the 98 value to 66 and so forth. And any quick math, how far apart are those? So it's always 32. Like uppercase to lowercase is always, wonderfully, good design, 32 away, one from the other. So what does this mean? Well, I think we saw earlier that underneath the hood, a char is just a number. You can certainly do arithmetic on it. And here again, if you understand these lower level primitives, what if I do this? Whatever s bracket I is, if I know on line 13 that it's lowercase, Do I want to add or subtract 32? So I want to subtract because I want to go from like 97 to 65 or 98 to 66. So indeed, if you do some quick math, that gives you 32. So it suffices to just treat chars as numbers, subtract the 32, and printing it with %C, I think will just convert lowercase to uppercase. If you now fast forward to like the real world, Microsoft Word or Google Docs, if you've ever chosen the menu option that forces things to uppercase or lowercase on occasion, literally that's what Microsoft and Google have done. They iterate over every character in the document, check if it's lowercase, and if so, they subtract 32 from it and show you the new value. What if, though, it is not a lowercase letter? I think I can keep it easy and just print out the current letter unchanged if my goal is to simply force things to all uppercase, and that letter then would be S bracket I. So let me go ahead now and make uppercase. Hopefully no errors. /uppercase. And I'll now type in David with an uppercase D, but lowercase everything else. But now the after version is David. An aesthetic bug. Notice here I forgot to include, just for prettiness' sake, a \n at the end. No problem. I'll add that. Let me fix my mistake. Make uppercase. /uppercase enter. DAVID enter. And voila. And I deliberately added another space after the after just so that they would line up pretty, even though before and after have different numbers of letters. Questions then on this implementation of forcing something to uppercase, which in and of itself is not all that enlightening, but is representative now of how you can leverage these low-level primitives. Question? No? All right. Well, this honestly is tedious. My God, like does Microsoft, Google, everyone, you have to literally write out this code just to do something simple? Well, no. That's again why we have things like libraries. And increasingly now for problem sets, projects, and beyond, well, you just use libraries more often off the shelf so as to solve problems that surely other people have had before you. So how can I now use this library, ctype.h? Well, let me go back into my code. Let me include this among my header files here. I tend, just so I can skim things easily, I tend to alphabetize my headers, but that's not strictly necessary. But it allows me at a glance to realize, did I or did I not include something I need? Now let me go ahead and do this. It turns out if you read the documentation for the ctype library, there's a function wonderfully called if is lower that takes in a character as its argument, essentially, so S bracket I. And if that returns true, a Boolean value, if you will, well, I'm going to force it to lowercase. But I don't have to do this math anymore. Turns out in the ctype library, there's also a function called toUpper that takes a character as input, like S bracket I, and it just does the math for you so that you can abstract away the 32 thing and just know that someone else has solved that problem for you. Otherwise, I can leave my code unchanged down below because I'm not changing anything else. So if I do make uppercase now, and then /uppercase, DAVID with just a capital D, and now it still works. But if you read the documentation further, it turns out that toUpper is smart. If you pass in a character to toUpper that's lowercase, it obviously converts it to uppercase by doing that math. But if you pass in a character to toUpper that's already uppercase, the documentation you would see tells you that it leaves it unchanged. So I can tighten all of this up. I can get rid of the whole else. I can get rid of the whole if, and arguably now implement a program that's just as correct, but better designed. Why? Fewer lines of code, easier to read, lower probability of mistakes. Assuming the library is correct, it just makes it easier and faster for me now to write code. So if I now do one last time, make uppercase, enter, /uppercase, and type in my name, still working. But now notice we've whittled this down to far fewer lines of code, albeit using now this additional library. Questions then on how we did this? All right, a few final building blocks for the